Hello, everybody. Thank you very much for coming to this talk. Well, coming to it, I mean, you know, it's virtual, so you didn't really come. But thank you for watching. I'm going to be talking about hyperbolicity and Turaev hyperbolicity of virtual knots. Virtual, there's the word again. How about that? So this is work done over with a couple of different groups of students over a period of time, but I think it has some interesting aspects that and I hope you find it interesting. Okay, so as everybody knows, or almost everybody knows, classical knots and links have diagrams that look like this, and we have a fundamental equivalence between them that we can use to tell whether or not two diagrams represent the same knot or link, namely, if they do represent the same knot or link, there has to be a sequence of Reidemeister moves like these three moves shown here to get from the one diagram to the other. So this is a fundamental equivalence between diagrams for knots. Now, Bill Thurston in 1978 proved that knots can be broken into three different types, and it's a very powerful result. You can have torus knots, namely knots that sit on the surface of a torus with no crossings on the torus. Those crossings that you see are from shining light through the torus, but there are no crossings on the surface of the torus. So you can have torus knots. You can have satellite knots. Now, what's a satellite knot? Take a knot, as you see on the left here, thicken it up, and then stick another knot inside it, so long as it wraps all the way around. That will end up being a satellite knot. Okay, so those are satellite knots. And then the third category is hyperbolic knots, and I'm just showing you one example of such a hyperbolic knot. Okay, so knots can be broken into these three categories, and they're separate. Okay, so we have a bucket for torus knots, a bucket for satellite knots, and a bucket for hyperbolic knots. Every knot ends up in one of these three baskets. But what exactly do I mean by hyperbolic knot? So I'll say a knot or link L is hyperbolic if any of the following three options hold. They are actually equivalent to each other, not obviously so. We say that the knot is hyperbolic if its complement can be given a metric of constant negative curvature -1. So a way of measuring distance that has constant negative curvature -1. Equivalent to that is that its complement can be glued together nicely out of ideal hyperbolic tetrahedra. Now, what do I mean by nicely? I mean that for each edge of one of the ideal tetrahedra, when I glue them together, I will get a full 360 degrees of angle around each edge after I do the gluing. And I also have to worry about something called completeness, making sure that I actually get a complete metric, which has to do with the missing vertices of the ideal tetrahedra. Number three, I can also state it as there exists a covering map from hyperbolic 3 space to the complement such that the covering translations are all fixed point free isometries. So let's look at an example that actually ties these three together. This is the example of the figure 8 knot complement. So here's the figure 8 knot you see on the bottom, and the green material here is supposed to be the complement, 3 sphere minus the knot. And upstairs, I'm using the upper half space model of hyperbolic space. So that is the set of all points above the plane, the XY plane in 3 space, and then I'm putting a hyperbolic metric on it, and I'm going to create a hyperbolic structure for the figure 8 knot complement by taking 2 ideal tetrahedra. These are actually ideal regular tetrahedra, all 60-degree angles between the faces, and I'm going to glue them together. So I glue them together obviously along the central face right here, which is an ideal triangle, and then I'm going to glue the other faces in pairs. So this back face labeled A gets glued to this front face labeled A prime, twisting it so that the edge labels match. The front face B gets glued to this bottom face B prime, and the back face C prime gets glued to this bottom face C. And now if I glue those all up, it's not at all obvious. It's the hard thing to see. That will give me the complement of the figure 8 knot. What that means is I can take the hyperbolic metric on hyperbolic space, and I can then yield a metric for the complement of the figure 8 knot. So the figure 8 knot inherits that metric that I have on hyperbolic space. So that, remember, was my first possibility for how to describe the hyperbolic structure on a knot complement. You'll also notice that I have 2 ideal tetrahedra that I'm gluing up in order to get the knot complement, and so that was our second definition, possible way of describing a hyperbolic structure. And if you look, you'll see that I have 6 edges labeled 1 that will all be glued together, and 6 edges labeled 2 that will all be glued together, ultimately in the original 2 ideal tetrahedra. So the full angle, since all of those angles were 60 degrees, the full angle will be 360 degrees around each of the edges. And then Finally, the last way to describe hyperbolic structures, we said we have a covering map from hyperbolic 3 space to the knot complement. In this particular case here, you see I have the 2 ideal tetrahedra. If I took another copy of this tetrahedron and glued it to the face A prime, I'd have another tetrahedron over here, and I would continue to glue more and more copies of these tetrahedron, and eventually I would tile all of hyperbolic space, and then I would actually know how to create my covering map, because all of the tetrahedra that came from this left tetrahedron here would all project down to the same single tetrahedron making up the complement, and all the ones that corresponded to the other tetrahedron would also project down to a single one, and so ultimately I would get a covering map of all of hyperbolic space down to the knot complement. Okay, let's take a commercial break, all right? We've done a lot of work here, so let's take a quick commercial break. I want to tell you about a different piece of work. This is actually 2 papers that I am co-authoring with Bill Meeks and Alvaro Kruger-Ramos. And this is called Modifications Preserving Hyperbolicity of Link Complements. And I wanted to mention this because some people interested in hyperbolic 3 manifolds may find this useful. So first off, we're going to have 2 moves that we can do on hyperbolic manifolds that are link complements that will preserve hyperbolicity, and that's really what this is about. So the first one's called the chain move. So suppose I have a link in a 3 manifold with hyperbolic complement, and I'm going to assume that the link locally looks like this. So there's some ball in the manifold such that one component of the link is coming through like this, another component, or possibly the same component, goes through a second time, and then I've got a trivial component that wraps around them. Now, famous fact, useful fact from hyperbolic 3 manifold theory is anytime you have a twice punctured disk, it's totally geodesic. So this is a nice situation to find yourself in. And what the chain move says is you can take this situation and replace the single component here by 2 components, and you can put in as much twist as you want as well. So K represents the number of twists in this little part of the second component. Okay, so anytime I can do that, anytime, with only a few exceptions. So the complement of L prime, this new link complement, will be hyperbolic with only 3 exceptions. And the 3 exceptions are if outside of that ball that I had with the trivial component in it, I have a rational tangle, and the rational tangle is the rational tangle 0, the rational tangle -1, or the rational tangle -2, 0. Okay, so I'm sorry, I said that wrong. The rational tangle minus K, or the rational tangle minus K plus 1, or the rational tangle -2 minus K. In all 3 of those cases, you can simplify the manifold, because remember I had K twists up here. This will undo those twists, and I will just get this link complement, or this link complement, or this link complement, all of which are in fact not hyperbolic. But those are the only 3 exceptions. So once you tell me a given K, I have 3 exceptions for each K, which correspond to the rational tangle of the outside being -K, -K plus 1, or -2 minus K. Okay, now here's a second move called the switch move. In the switch move, again, I have a link in a 3 manifold such that the complement is hyperbolic. And I assume I have a simple geodesic that goes from cusp to cusp. So right here is a part of the link complement. Here's a part of the link complement. This is a simple geodesic in the complement of that inside some ball in the manifold like this. Then what I'm allowed to do is replace that local picture, the one that looks like this with the 2 link components passing through that ball, with a picture like this. Okay, so now I have a trivial component in addition to switching the gluing, how my endpoints are glued together in the link complement. Now, why do I care about this? Well, the advantage is, you remember the chain move, I only could do it in a case that I had a situation that looks like this. So this sets me up for doing the chain move. So this is one of the reasons why it's useful to have the switch move in addition to the chain move. Okay, back to our regularly scheduled programming. So anytime you have a hyperbolic knot, it has a volume associated with it, and this is the Mostow-Prasad rigidity theorem. And so you can look at the tables of knots, and you'll see we have a trefoil knot up here. It's not hyperbolic, so we'll just put down its volume as 0. The 5-1 knot is 0, the 7-1 knot 0, since those are all torus knots, but the rest of these have hyperbolic volumes associated with them. The figure 8 having the volume 2.02988, which was proved by Meyerhoff and Cow to be the smallest volume of any classical hyperbolic knot. Okay, but the volumes are a very good way of distinguishing between the knots, very effective invariant. However, they're not a complete invariant. So for example, this is the first time two knots have the same volume. This is the 5-2 knot and a 12 crossing knot, and they both have the same volume. I know I have them only written out to this many decimal places, but in fact, you can prove they are the same out to an infinite number of decimal places. So it's not a complete invariant, but it is a very powerful invariant. How do you tell if a knot is hyperbolic? Well, Bill Thurston proved that a knot or link is hyperbolic if its complement contains no essential spheres, annuli, or tori. So if you can eliminate those three possibilities, then you in fact know that your knot or link is hyperbolic. And that's in fact how you ultimately prove that all knots fall into those three categories that we mentioned: torus knots, satellite knots, and hyperbolic knots. Now Monasco used this to talk about a specific category of knots. Namely, he proved using this fact that if K is a prime alternating knot or link that is not a two braid, then in fact it is hyperbolic. And in fact, he is not holding a two braid there. I think that's a 5-2 knot that he's holding right there, which is hyperbolic. So this is also a nice theorem because it's saying this large class of knots are all hyperbolic. As an example, this is a link. It has, I think, 992 crossings. I got bored on a plane one time and I counted them, but it is alternating. It goes over, under, and it turns out you can also tell that it's prime. Bill Monasco proved that if it's not prime, there would have to be some circle in the plane that crosses the link only twice with the crossings to the inside and outside, and you can see very easily from the diagram here that that is not the case. So this is a hyperbolic link, just in case you ever need to know that. So can we generalize beyond alternating knots? Can we extend Bill Monasco's results? And this is work of the SMALL Knot Theory Group 2017. SMALL is a program we run at Williams College, funded by the National Science Foundation in Williams College, where we bring students in to do original research on mathematics. And this group included the people here. Luya was an undergraduate at Princeton. She's now at Berkeley. Beatrix, Carlos was at Harvard. Beatrix was at Williams. Braden was at Haverford, now he's at Boston College. Dashiro was a Williams student, and Ziki, who goes by Canvas, was at Williams and is now at Stanford. It's a very strong group. And we looked at links in a surface cross I. So instead of looking at links in the three-sphere, we looked at links in a surface cross I. So surface cross I, just a thickened surface, and so I've got a link in a thickened surface. Now, we were not interested in the actual topic of this talk. We were interested in something else. Namely, we were interested in tilings on surfaces. And so it turns out that if you have a tiling in the plane and you replace it with a link like this, then you can generate a link living in a thickened torus, because the plane, if you have a periodic tiling of the plane, it will project to a tiling on the torus, and so therefore you can create a link living in a thickened torus. And then you can look at things like the volume of the link divided by the number of crossings, and that's what these numbers on this side are actually referring to. So this was work where we were very interested in this question of the volume density, the volume of the link divided by the number of crossings. And so these examples on the left-hand side are all examples of what are called tiling links corresponding to these particular tilings in the plane. These are all genus 1 in the sense that they generate links living in a thickened torus. But you can do the same construction instead of using the Euclidean plane, using the hyperbolic plane. And when you do that, and then you quotient out by symmetries, you actually get a tiling on a genus 2 or higher surface, and you can still find the hyperbolic volume and divide it by the number of crossings. And so here you see these numbers here that corresponded to this. This was joint work with Aaron Calderon and Nat Mayer, who were both part of SMALL 2015. And that's what was motivating our interest in these links living in thickened surfaces. So what we proved in 2017 is the complement of a prime fully alternating link in a surface cross I is hyperbolic. Okay, I'm assuming here right now that the surface is orientable and the genus is greater than or equal to 1. So this generalizes Manasco's result, except I haven't yet told you what fully means. But if you have a prime alternating link, fully alternating link, and a surface cross I, it will in fact be hyperbolic. Now, what's a fully alternating link? That just means that it's alternating and all of the faces of the projection surface are disks. So I don't have any annuli wrapping around my surface. I don't have anything like that that doesn't touch the link. So all of the faces of the projection surface are disks. We also had a generalization of Manasco's result about primeness. We said a fully alternating link in S cross I is prime. You want to know this because you'd like to be able to apply the theorem. If and only if there's no disk hitting the projection, disk living on the surface that hits the projection in 2 points with crossings inside the disk. Okay, so this is parallel to Manasco's result for how you tell whether an alternating link in the plane is prime. This is the analogous result on a surface. So what this means, once you know that they're hyperbolic, is we can associate volumes to them. So we can associate volumes for any prime fully alternating link in a surface cross I. Now, you might say volumes, well, but I thought you only computed volumes when you didn't have surface boundaries, when you only had either a compact manifold or you could have a manifold with torus boundaries and you removed the tori. But in fact, how we're going to deal with that is we're going to assume that the surfaces of genus greater than or equal to 2 are totally geodesic in the hyperbolic structure. And then that gives a unique hyperbolic structure that's associated to the surface cross I, the link complement in the surface cross I. And in that case, we call the link TG hyperbolic, TG standing for totally geodesic. Okay, now I want to talk about virtual knots and links. So this is an idea that was created by Luke Hoffman in 1999. And he extended the idea of knots to what are called virtual knots. And virtual knots are like knots in the sense that they have classical crossings where one strand crosses over another. But we also allow these things called virtual crossings, which are the ones shown here with little circles around them. And so these are examples of virtual knot diagrams. And then we have to come up with an equivalence between different virtual knot diagrams. And the equivalence is going to be an extension of the Reidemeister moves. So for the Reidemeister moves, those still hold because we still have classical crossings. So the standard Reidemeister moves will be applied to these diagrams. But then we also have these virtual crossings, and we will have corresponding virtual moves. So the type 1 classical Reidemeister move also has a type 1 virtual Reidemeister move. Similarly, the type 2 classical Reidemeister move has a corresponding virtual Reidemeister move, and the type 3 classical move has a corresponding virtual move. But we also have to worry about interaction between the classical crossings and the virtual crossings. And so here we see that we can do a move where if we have 2 virtual crossings by a classical crossing, we can slide the virtual crossings past. So that's allowed. There is another move that's not allowed called the forbidden move, and that would be the opposite of this one, where instead I had 2 classical crossings, maybe these are both over-overs, and I had a virtual crossing here. I am not allowed to move that past. Now that's somewhat counterintuitive because you say, well, look, it looks like it ought to work, but that's the rule, okay? So don't do it. Okay, so this gives us an equivalence between virtual knot diagrams, and therefore we now have a theory of virtual knots. Now, Kamada and Carter-Kamada and Saito in 2000 turned the theory of virtual knots into an equivalent theory of what are called surface link pairs up to stabilizations and destabilizations. Now, what do I mean by that? Here's what is called the virtual trefoil. So it's like a trefoil diagram where I've turned one crossing into a virtual knot. And I'm going to create a surface called a ribbon surface that knot lives on. Okay, so that's going to look like this. And the way I'm creating this surface is I'm putting a little disc in at each of the classical crossings. I'm putting a little ribbon in along these parts right here, along the strands of the knot that connect these classical crossings. And then when I put my ribbon in here, I'm going to pretend there's no crossing there at all. And so I will take the one ribbon and cross it over the other ribbon. So virtual crossings don't get a disc associated to them. And you essentially just finish off your surface as if they weren't there, your ribbon surface as if they weren't there at all. Okay? So disc, disc, ribbon, ribbon, then ribbon ignoring the crossing, the virtual crossing and ribbon ignoring the virtual crossing. Now you might say, well, what if I pass this under or over? Who's to say which one to use? Doesn't matter. This is a topological construction. We don't care about the embedding in space that corresponds to this surface. So in terms of what we get up to homeomorphism, it makes no difference at all. Okay, now I'm going to cap off that surface, and when I cap off that surface by filling in disks along the boundary components, in this case 2 boundary components, I get some surface that my new link, that a link projection lives on. In this case, the surface that I get will be a torus. You'll notice, because I put disks around each of my classical crossings, the classical crossings will appear on the surface, but the virtual crossings will not. The virtual crossings now become an artifact of, if I project down the torus, you'll see there was a strand. Because my ribbon went over the other ribbon, there'll be a crossing that's created by that, and that's where my virtual crossing comes from, okay? Now, so I can talk about just having knots and links living on surfaces. So this is a surface link pair, and the genus could be whatever it is. And then I'm going to have equivalence that corresponds to just isotopy of the knot or link on the surface, but I'm also allowed to add handles to the surface or subtract handles from the surface if the knot is not containing them. And so that's what we mean by its equivalent modulo stabilizations when I add handles, and destabilizations when I remove them. Okay. And we'll call the virtual genus of a knot to be the least genus generated over all the projections of that knot. So keep in mind that each projection of the knot here will generate some knot or knot living on a surface, and therefore we'll say the virtual genus is the least genus for any projection of that knot. Now those Reidemeister moves that we were talking about before can now be seen in the context of these surfaces as corresponding to just a part of a surface up above, another part of a surface down below, and when I project down, I see this kind of type 3 situation. In this picture, I don't have the circles drawn in for the virtual crossings, but they're intended to be there and there. And then if I just move this past upstairs in the surface before projecting, that will be equivalent to the virtual Reidemeister move that allowed me to take 2 virtual crossings and move them past another crossing. Similarly for the other virtual Reidemeister moves. Okay, so let's take a look at some virtual knots. This is a table of virtual knots that was created by a student of Dror Bar Natan's. This is a list of the distinct virtual knots up to 3 crossings. You'll notice in the category of virtual knots, we include classical knots. So there you see the trefoil right there is one of the knots. Then we're looking now at virtual knots with 4 crossings, and you'll see there's up to 40 on this page, and then it continues on up to 108 knots. You'll notice the very last one is the classical figure 8 knot, okay? So we have 108 virtual knots of 4 crossings. If you add in the other knots that we saw previous to this, it turns out to be, I think it's 117 virtual knots of 4 or fewer crossings, not including the trivial knot. And if you exclude the 2 classical knots, we have 115 virtual knots, non-classical virtual knots of 4 or fewer crossings. So things have exploded as compared to the classical knots, of which we just had 2, the trefoil and the figure 8. So there's many, many more of these virtual knots. Now, Greg Cooperberg in 2012 showed that every virtual link can be represented uniquely as a classical link in a minimal genus thickened surface. So if you do this construction that we talked about, where you consider all the different projections of a virtual link and you try to find the one that has the least genus, the one that you find that has the least genus will be a unique representation as a classical link in that minimal genus thickened surface. So that's very useful to us. In the case that we have that thickened surface minus the link is TG hyperbolic, then we can compute the hyperbolic volume. So we can associate to a virtual link a hyperbolic volume. And so the corollary is if a virtual link diagram for L, any link diagram for L yields a TG hyperbolic link complement in a surface cross I, then we can calculate the hyperbolic volume. And it also turns out that the genus of the surface will be the virtual genus of L. And the reason for that is because otherwise, if that weren't the case, you would be able to, if it weren't the case, there would be an essential annulus that would allow you to cut and to simplify the surface down to a lower genus, but that also would mean that it was not hyperbolic. So this is a way of determining virtual genus, if you can show that a particular link complement in surface cross I is TG hyperbolic. Okay, so let's be more specific about TG hyperbolic. I mentioned it before, but let me be very clear. A compact orientable 3-manifold is TG hyperbolic if, once I cap off any sphere boundaries with balls, I discard any torus boundaries, just shave them off, then the resulting manifold has a finite volume hyperbolic metric such that all remaining boundary components are totally geodesic. So I'm looking for a hyperbolic structure, for instance, on this knot complement. You'll notice when I remove the knot complement, that corresponds to sort of shaving off a torus boundary. And then I've got an inner genus 2 surface and an outer genus 2 surface. And I need both of those to be totally geodesic to inherit a unique structure on the corresponding link complement. All right, so let's look at our first example. This was the virtual trefoil again. The virtual trefoil, when I create its ribbon surface, which then becomes its surface link pair, I get this link, this knot living on the torus. I'm going to think of this as a knot living in a thickened torus, and that's going to be genus 1. And then I can compute its volume, and its volume turns out to be 5.333489 ... So I can calculate its volume out to some number of decimal places. So that's the volume of that particular one. Notice there's nothing totally geodesic here because it doesn't have any higher genus boundary. It just has 2 torus boundaries that have been shaved off. Conjecture is, and this is still open, that this is the smallest volume of any non-classical virtual knot. That that's the smallest you're ever going to get, but that has not been proved. Now, the claim or the theorem is that if I have a prime alternating virtual knot, we'll have to be careful what prime means, but a prime alternating virtual knot, and it's a virtual knot that's alternating, namely as you travel around the projection of the knot, it goes over, under, as you ignore the virtual crossings. So it's over, under in the classical crossings. That will generate a TG hyperbolic link in the corresponding thickened surface. So all of those will, in fact, be TG hyperbolic. And it follows immediately from the aforementioned theorem because of the fact that when I lift up to my surface, my knot or link will be alternating on that surface. So all I need to know is that it's prime because it will be fully alternating on that surface. Okay, so for example, here is a virtual knot. You'll notice this one's alternating. I go over, under as I travel around, ignoring the virtual crossings. And this one has genus 1 and has a volume 9.503. I can calculate it. So it's definitely, I mean, it is hyperbolic according to the theorem. Here's a whole set of examples, which are called the n-polygonal virtual links. I've got virtual crossings on the inside. Just ignore the blue. I've got virtual crossings around the inside polygon, and around the outside, I've got classical crossings. And you'll notice these are all alternating virtual links because as I travel around, I go over, under, ignore, over, under, ignore, over, under, ignore. So all of these components are in fact alternating. Therefore, by the theorem, this will be TG hyperbolic for all n greater than or equal to 3, and I can actually calculate the genus from this. So knowing it's TG hyperbolic tells me that the genus will be the genus that I get from the diagram that's alternating. Now, how do you go about computing the volumes? Well, what you do first is I'm looking at this particular example right here, you figure out how to put that on a surface, the corresponding surface. So this is one of many Blackboard pictures we did in summer of 2018. And then what I'm going to do is I'm going to take this picture, which remember is a knot or link in a thickened surface, and I'm going to double it. And when I say double it, I mean I'm going to take a second copy, a reflection of this thickened knot living in a surface, and then I'm going to glue one of its boundaries to the outer boundary of this one and the other boundary to the inner boundary of this one. So originally I had a surface cross I. By doubling, I'll get a surface cross a circle. And instead of having one component inside the surface cross I will have 2 components inside the surface cross a circle, one component being the reflection of the other component across either one of these two surfaces that we're talking about here. So now I'm living in a surface across a circle, and I want to represent that in a way that the computer program SnapPy can keep track of it. And so I'm going to use the fact that a surface across a circle can be represented by a link that looks like this, where you do 0-1 surgery on all the components. That will give me a genus G surface across the circle. So now what I'm going to do is I'm going to take my original link living in the surface. I'm going to represent it in SnapPy. You'll see the components that corresponded to that picture. These are all the components, the green, the purple, the red, the blue, that I'll be doing 0-1 surgery on. And then the yellow and the brown components are the link and its reflection in what will ultimately be my surface across a circle. So I'm going to input this link into SnapPy. I'm going to do 0-1 surgery on all but these two components right here. That will then generate the link that I want in a surface across a circle. And then I'll get a hyperbolic volume from SnapPy, and then I'll take half of it, because remember I did reflect initially. I doubled my manifold across those boundaries, so I only want half of that. I take half the resulting volume, and that's how I compute the volumes. So let's look at some examples. Here is, again, the trefoil. We've already seen that example with volume 5.33349. Here is the virtual knot 3.1. This is a genus 2 knot, and it has a volume, so it now has two totally geodesic boundaries in the thickened surface, and it has a volume quite a bit bigger, not so surprising, 18.7531. This is the virtual knot 3.2, which you might call the virtual figure 8 knot. That is genus 1 with a volume of 7.0791. This is the small group from 2018, and all the work I'm talking about now was done by this group. Jonah was at Williams, Kabir was at Cornell, he's about to start at Berkeley next fall. Yi was at Columbia, he's now at UPenn in graduate school. Jen was at USC, she's now at Boston College for graduate school. Or is at Harvard. Kate was at College of New Jersey, now at Rice. And Natalia, who actually won the Alice T. Schaefer Award for the best woman undergraduate in the country, very talented. And she was at Harvard, and she will be going to Yale after taking a year in Copenhagen on a Fulbright. Very good group of students. Okay, what about non-alternating virtual knots? Well, we proved the following fact. If you have a prime 1 virtual alternating knot, it'll also be TG hyperbolic, and its virtual genus will be 1. Now, what do I mean by a 1 virtual alternating knot? Take an alternating knot diagram and change one crossing to be virtual. That'll be a 1 virtual alternating knot. So long as the result is prime, it will be TG hyperbolic. Another example is the famous Kashino knot. Now, the Kashino knot is famous because it is a virtual knot that is a composition of 2 trivial knots. If I cut this open along here, I could undo both halves. They're both trivial. So that's very different than what happens for classical knots. And you can calculate its hyperbolic volume, namely it's this, and it has a genus of 2. Moreover, if you do a generalized Kashino knot, and you can pick the crossings any way you want in any of those places, you can actually then prove that it will always be hyperbolic. More generally, if you take any knot that's TG hyperbolic and you compose with one of these little Kashino summands, that will increase the genus by 1. So here's where you see the genus increasing by 1, and you will again get a knot that is TG hyperbolic. So composition by Kashino summands actually preserves hyperbolicity and increases genus by 1 every time. So here's an example of that where I have a Kashino summand on another knot right here. And so this is an example where that would be true. So let's take a look at the volumes of TG hyperbolic knots of 4 or less classical crossings. So I know you probably can't see this that well, but I can tell you what's in here. So this is the set of all of those 115 knots that I mentioned before. And these are the volumes that we computed that summer. And I will show a close-up of this because I realize this is impossible to see now. So let's look at a, oh, and sorry, I didn't say this. Of the non-trivial virtual knots of 4 or fewer crossings, all but one of them are in fact TG hyperbolic. Now this is surprising, right? Because remember, when we saw the table of classical knots, we hit a bunch of these torus knots relatively quickly, and so there were plenty of non-hyperbolic knots in that list, whereas here in the list through at least 4 crossings, pretty much all of them are hyperbolic, are TG hyperbolic. And so that's a very promising fact that says that TG hyperbolicity should be very useful for understanding virtual knots. Here's a close-up of part of the list, starting with the virtual knot 2 sub 1, which was the virtual trefoil with the volume 5.33349, minimal genus, 1, 2, 1, 2, 1, 2, 1. This one says 0. That's because this is the classical trefoil, which means it lives in the 3-sphere, and it lives in the 3-sphere, and it's not hyperbolic, as we know. Okay, and then we see these numbers going up. Now, an interesting thing to note here is that quite a few of these volumes are identical with other volumes. So, for instance, 3.3 and 3.4 have the same volume. 4.2 has the same volume as 469, 476, 498. Why? Don't know. Very interesting question. Why are there these sets of knots, all of which have the same volume? Here's an example, 4.3 and 4.6. You can stare at those diagrams for a while, and I don't know why they have the same volume. So I think it's very interesting. That's an interesting problem to work on. What can we say about the minimal volume virtual links? Well, the smallest volume non-classical virtual knot, as I mentioned before, is unknown, conjectured to have a volume of 5.33349, but it's not known. We do at least know the minimal hyperbolic volume of a virtual link of 2 components, and that's given by this link right here. So this link right here, which is a genus 1 link, and the trick is, when I realize it is a genus 1 link, it's in a thickened torus, which is the same as taking the complement of this Hopf link in the 3-sphere. So I can actually get a 4-component link in the 3-sphere that corresponds to this particular link. And any link in the, any genus 1 link will actually be the complement of any genus 1 2-component link will be the complement of a 4-component link in the 3-sphere. And we happen to know by work of Yoshida that the smallest possible volume of a 4-cusp manifold is 7.3277. And we can prove that that is in fact the smallest volume of a 2-component virtual, non-classical virtual link. All right, now I want to talk about Turaev surfaces for just a little bit. So this is a slightly different construction. Turaev surfaces look something like this, but I think I'm going to work with a different construction other than that one. And the idea is going to be very similar to what we did before. We take a projection of our knot or link, and we're going to create a ribbon surface. The only change is going to be that we'll put a few twists in it. So if I have a region of my projection diagram where I have an undercrossing going to an overcrossing, no twist. But if I have an undercrossing going to an undercrossing, I'm going to twist this way. And if I have an overcrossing going to an overcrossing, I'm going to twist this way. So we're generating a ribbon surface, but now it has additional twists in it. And then I'm going to cap off the boundaries with discs, so I get a closed surface, just as we did before. Now, this is the Turaev surface. Now, the Turaev surface turns out orientability is a little trickier. For classical knots, the Turaev surface is always orientable. But for non-classical virtual knots, sometimes it's orientable, sometimes it's not. An easy way to tell is the Gauss code, where we travel around the knot and we write numbers on each of the crossings and write down all the numbers. And so we travel around the knot, we get 1, 2, 3, or whatever. Okay, I get a pattern of these numbers. And you'll notice for a classical knot, there will always be an even number of digits between 2 appearances of a given digit in the list. Okay, so between any 2 copies of an integer, there's an even number of integers. For non-classical knots, for virtual knots, I can have either situation. I can have it the case where it is still true that between any 2 copies of a given integer, there's an even number of integers. That will generate an orientable Turaev surface. However, if I have 2 digits that are the same and an odd number of digits in between, that will generate a non-orientable Turaev surface. Okay, if I have a projection of a knot that yields a knot in a thickened Turaev surface that's hyperbolic, we're going to call that Turaev hyperbolic. And again, we'll be assuming TG hyperbolic boundaries. And this is the interesting theorem. So if I start with a prime non-2 braid, remember we excluded that when we were from work of Monasco, classical or virtual projection of a knot, I don't care which, so long as it's a prime projection, we'll come back to that in a second, that will generate a prime fully alternating knot in the thickened surface. And so it will be Turaev hyperbolic. The point is those twists that I put in my ribbon surface were designed exactly to make sure that the resulting projection would be alternating on the surface. So I'm assured of getting an alternating knot or link in my thickened surface, and assuming it's prime and not a two braid, that also assures that it'll be TG hyperbolic as I need, okay? So again, as I said it, the Turaev link is fully alternating since we made it by twisting the connecting band so it would be alternating on the surface, and we capped it off so it is fully alternating. And then our theorem from Small 2017 says that it is hyperbolic. These are our two exceptions. This one is, as I mentioned before, as Manasco said, is not hyperbolic. And then this is a two braid in projective plane. That also is not hyperbolic. But except for those, assuming it's prime, you're good to go. In fact, that actually proves that every classical and virtual knot or link has a Turaev hyperbolic projection. So this includes the trivial knot, the trefoil knot. We can actually associate Turaev hyperbolic projections to everyone. How do I do that? The only thing I have to worry about is non-primeness, right? Because we already said, so long as our diagram, when we lift it up, it'll be fully alternating whenever we start with a Turaev surface. So we just need to find a projection so that the link is prime on the Turaev surface. And the trick is, if I have some circle that's crossed twice by the knot or link with stuff inside and stuff outside, I'm just going to do a type 2 Reidemeister move here, or I might have to worry about virtual crossings in between. Here, I do that, and I've destroyed that circle. It's no longer crossed just by two things, it's crossed by more. And when I do the Turaev construction, when I get to my Turaev surface, the link will no longer be composite. It will now be prime. Okay, so I can associate a Turaev volume to any classical or virtual knot or link. Okay, and that will be the minimum hyperbolic volume that I get for all Turaev hyperbolic projections. Since every knot or link has a Turaev hyperbolic projection, I'll just take the minimum one. That'll be the volume. And we'll say the classical Turaev volume of a classical knot or link is the minimum hyperbolic volume over all classical Turaev hyperbolic projections, namely projections that do not allow virtual crossings. Notice Turaev volume will be less than or equal to classical Turaev volume, since classical case is more restricted. Okay, so let's take a look at the trivial knot. Here is a projection of the trivial knot, and its Turaev volume turns out to be 9.503. Here's another projection of the trivial knot. Its Turaev volume is 12.077. Here's another one. Its Turaev volume is 16.880. And here's one even of genus 2. Its volume, of course, as genus goes up, gets bigger. It's 33.596. The conjecture, we haven't proved this, but the conjecture is that this one right here corresponds to the classical Turaev volume of the trivial knot. Do we know some Turaev volumes of some knots and links? Nope, sorry, we don't know that yet. Do we know any classical Turaev volumes of some knots and links? Yes. So for instance, the twist knots, we can actually figure out their classical Turaev volume. In this case, because we're restricting to classical, all of our surfaces will be orientable. So we only have to worry about surface cross I where S is orientable. Miyamoto actually gave a lower bound on volume of links in a surface cross I, actually in more general case where you have higher genus surface. And from Miyamoto, we know that the link volume will be at least 7. The link volume for a link for genus greater than or equal to 2 will be at least 7.3277. So it turns out that then if I have a knot in a torus cross I, as we mentioned before, that will be a knot in the complement of a Hopf link. So it's at least a 3-component link in S3, but Agel proved that links of 2 or more components have a volume of at least 3.6638. Therefore, we can just use the volume in the 3-sphere of all of these. These are all hyperbolic knots, and the volumes in the 3-sphere are all less than 3.6638, which is V oct, the volume of an ideal regular octahedron. And therefore, any non-alternating diagram will yield a higher genus Turaev surface, and so therefore the volumes of these are the volumes that are the classical hyperbolic volumes of these knots. We also know the classical Turaev volumes of these particular link complements. And this uses both the Miyamoto and Yoshida's lower bounds on 4-component link complements. Let's go back to the trivial knot for a second. As we said, we think the classical Turaev volume is 9.503. That's a conjecture. But what if I allow diagrams with virtual crossings in them? So for instance, this diagram right here, if I turn that into a Turaev surface and then into, and then cap off the boundaries, I end up getting a link complement in the Klein bottle. So this is a link complement in a thickened Klein bottle. It's actually a twisted I bundle in the Klein bottle. And it turns out its volume is 2 times the volume of an ideal regular octahedron, 7.3227, which is less than this volume right here. And this one here is the conjectured Turaev volume. So we don't know, but that's what we think it is. Okay, so I think that's all I wanted to say. Thanks very much for listening, and I hope everyone is doing well. And I look forward to actually getting to see you in person at some point. That's it.